Hey there, guys. This is Miss Duffy, and this is P1063 Notes. We're going to be talking about work, energy, and power today. All right, so before we start, what does work do? Let's actually talk about what is work. So, number one, we're going to start with work. The symbol for work, I'll get my pencil going here. The symbol is, of course, W. But it can also be change in energy because, guys, work and energy are synonymous, okay? The units, because it is, of course, energy, are joules. Okay, so that's J. And we know the units could also be, remember that 1 joule is equal to 1 Newton meter. That's going to help us when we talk about what the formula for work is. All right, so what does work do? What are we talking about? Well, if it is a change in energy, all right, if it is a change in energy, that means it is transforming from one form or system to another. Okay? So let's talk about it. We also know that work, which is energy, is also a scalar. That means it's not a vector, which means it doesn't have a direction. But remember what I said earlier. Work can be positive, work can be negative, but we need to define what it means for something to be positive or negative. So for a force to do positive work, it has to be, and this is going to be a weird one to think about it. To do positive work, we are talking about work being defined as F dot D. And we've talked a little bit about a dot product before. In other words, we're talking about the component of the force that is parallel to the object. So if we've got a force acting on an object that's doing this, and it's traveling over a distance in the same direction, then F dot D is just FD, okay? But if we have something traveling along the ground and it is going a distance this way, but the force is at an angle, then what we have to do is we have to think about which component is parallel to it. So this component, here's my angle, so this is going to actually be F cosine theta. So what we know is for it to be positive, in other words, going in the same direction as the block is going, the force is, causing it to go in a positive direction, D, that angle has to be acute. Okay, think about that. It has to be less than 90 degrees with the horizontal, and we'll look at why that is. So for a force to do positive work, the force must be acute with the object's displacement. And we see that. Okay? Positive work is going to cause the system's energy, total energy, well, I'm waiting for you to predict it. Is it going to go up? Is it going to go down? Is it going to stay the same? So if you push on a block, you're feeding energy into the system. So positive work is energy into the system, which would cause the total energy to go up. Now, if you're doing negative work, that would mean that you think the force is obtuse with the displacement. I want you to think about why that would be. Now, you don't have to write this on your notes, but I wanted to show you over here. So if the displacement of the box, if the box is going some distance d, but the force is, in other words, it's going this way, but the force is going the other way, this angle would indeed be obtuse. It'd be greater than 90 degrees, wouldn't it? So what does that mean? If we break down and we look at the parallel version of it, which would be f cosine, right? Then what we're looking at is it's going to be in the opposite direction of the displacement, okay? So it's working against the forward motion. Now does it make sense why it would be obtuse? I hope so. So negative work causes the system's total energy. I bet you can guess what this is going to be. To decrease. Now, for force to do zero work, it can have no work in the parallel direction. So no work in the parallel direction would be kind of like this. See if this makes sense. If the block is going this way, but the force is going that way. Well, guys, that is there is no horizontal component, no parallel component. So the force has to be perpendicular. Okay? And if it does no work, then the total energy does not change. Doesn't say the object doesn't move. It just says that the total energy doesn't change. Okay? So now, state the equation for work done by a force F that acts through a distance d. We already said that work is equal to what we call F dot d. And if you've been in any kind of class that had vectors, you've done a dot product. Well, F dot d is the same as saying F parallel d, which in this case would be F, as we've seen, cosine theta times d. Okay? This is the parallel component. Okay? So this is going to be the force doing the work. This is going to be the angle with displacement. In other words, between F and D. And this is going to be the displacement while the force acts on it. So the big thing to remember, though, is this F dot D is really F parallel. So it's only the force in the same direction as the displacement itself. Good thing to know, regardless. So how can work be calculated from a graph? Well, it depends. A lot of times we look at force over its what? Displacement. Force over displacement. If we're talking about force over displacement, this is multiplied, right? So guess what? Anytime you have an x and a y that's multiplied, that corresponds to an area under the curve. So it is the area under an F versus X graph, okay? So if we were talking about this, if we had a force that was going, if our graph looked like this, then the work would be right there. The work would be equal to the area. Okay? Because it's change in energy. Now, we only do this if the force varies. Okay? So now, what's the work energy principle? The work energy principle says this. The mechanical energy you start with has to be the mechanical energy that you end with, the final mechanical energy, if, in general, okay, if it's a conservative system. Now, if we're introducing work, then what we can say is this. We can say that it is the energy we start with, the initial energy, plus energy from work is going to give us our energy final. Okay? Now, that energy from work can be positive or it can be negative. If it's friction, for example, it would be negative. If it's a push or an applied force, it would be positive work. So you really have to think about whether it's bleeding energy out or putting energy in to the system. So now state the work energy principle for a system of objects in a symbol equation and a word equation. Okay, so let's look at our word equation. Symbol equation, well, we know initial mechanical energy equals final mechanical energy, right? So we know we're going to have K initial plus U initial plus whatever work we do equals K final plus U final. So what does that mean? Starting energy plus this would be our net work on the system is equal to ending total energy. Okay? Now, what is power? Power is really easy. Power, which by the way is the symbol big P, not to be mistaken for lowercase p. Lowercase p is something else. Power is the rate at which work is done. Okay, guys, the rate at which work is done. Or in other words, how energy, the rate at which energy, as a separate definition, is transferred. So we can look at it this way. And by the way, the units, and I bet this is going to sound familiar to you, is watts, big W. Watts. You go look at the power meter on the back of your house and it's in kilowatt hours, okay? So it's clicking however long, okay? So now, what is the equation? So the equation here is going to be power is equal to the transfer of energy over time, or we can think of it as the work done over time. So if we look at this as an alternative to units, we know this is joules and this is seconds. So it can also be 1 watt is equal to 1 joule per second. Okay? Joules per second. So when you talk about a light bulb being 60 watts, you're talking about it is burning 60 joules per second of energy. That's why it gets hot. Okay? Incandescent bulbs get hot because it's literally a filament warming up, which causes the light. That's why LED lights are so much better, because it's not a filament of carbon warming up and exuding heat and heating up your house. It's just it's a different mechanism. Previous page said, work underneath the graph is the area under an F versus X graph. The next piece here. Next piece of the puzzle is a light bulb is rated at 100 watts. That means it converts 100 joules of, and it's electrical energy, isn't it, into light. Okay? And that's going to be every second. Okay? Because remember, it's joules per second. Electric motor delivers 500 watts of power to lift an elevator. That means the motor converts 500 what? 500 joules of, well, motor lifting it's electric, so electrical energy into what? Well, if it's lifting an elevator, that's going to be gravitational potential energy every second. Correct? Okay, so you try this one. A car motor causes a car to go from zero kinetic energy to 10,000 joules of kinetic energy in 10 seconds. The power delivered by the motor is what? Well, it's 10,000 joules for every 10 seconds. So the first thing we need to do is take that 10,000 and divide it by 10, and we get 1,000. So it's going to be 1,000 joules, right, per second, or 1,000 watts. That means the motor converts what? 1,000 joules of, and this time it's a car motor changing gasoline and turning it into energy, so this is going to be chemical. Bet you thought I was going to say electrical again. Chemical energy into what? Well, it's making it go faster, right? So kinetic energy every second. Okay? Hope you got that one. All right, so let's look at an example here. We've got a 1,000 kilogram car, and get used to doing this, 1,000 kilogram car. So we have a mass. There's our mass. And an engine produces a net force, so we have a force here. Okay, so this is a force applied, right? The car needs to go from 10 meters per second. Well, that's my initial velocity. 30 meters per second, that's my final velocity. How long? Ooh, how long? That means t equals, we don't know, to be for the car to gain the required speed. Okay, so let's look at this. What do we know? Well, we know a force on the car, don't we? Okay, well, we can, acceleration, if we know the force, we know the net force divided by the total mass. Well, the net force is 2,000 newtons, and divided by the total mass, which is 1,000 kilograms, we're going to end up with 2 meters per second squared, aren't we? That's my acceleration. So, to find the time, well, how do we find the time? What do we need to know? Well, we know its initial distance. X initial is going to be 0 because we don't know where it's at. We're going to say it arbitrarily starts at 0. So X final, we don't know. That's D of some sort, right? So what do we know? We also don't know time. Uh-oh, we don't know time. But if we can find a distance, how long does the on-ramp need to be? Oh, that's not time. Guys, I'm goofy. How long does it need to be? That's distance, D. So this is even better. So kinematics-wise, we are going to go with equation 3, aren't we? V final squared equals V initial squared plus 2A delta X. Well, delta X is going to just be D. V final is what? 30. So 30 squared equals initials 10 squared plus 2. That acceleration is 2. And we know this is D. So if we solve this, we are actually going to get 900 divided by, or minus 100 is 800 divided by 4 is 200. So we are going to get D is equal to 200 meters. So we've figured out how long the on-ramp needs to be. Now, why does that matter? Well, if we want to do a work energy, see, that kinematics is a pain. You had to think about, first you had to find the acceleration, then you had to figure out which kinematics equation to use. Well, let's look at this from a work energy solution instead. It's much easier. So, mechanical energy initial equals mechanical energy final. We are starting with kinetic energy. We are putting work in, right, due to an applied force, and we are going to get kinetic energy out. There is no potential because it didn't change heights, or at least it didn't tell us what height it was. So we know this is 1/2 mv initial squared, plus this is going to be the force applied over the distance, equals 1/2 mv final squared. Much nicer. Didn't have to go find the acceleration or anything. So what we know about this is we know this is 1/2. The mass of the car is 1,000. The initial velocity is 10. The force was 2,000. We don't know d, but we know this is 1/2. Again, the mass is 1,000, and the final velocity is 30. Guess what? If I work all of that out, you know what I get? D equals 200 meters. So sometimes a work energy solution is better, easier, faster. So now let's look at this guy. Graph shown to the right represents the force applied by a spring as a function of its stretch. Ooh, look what we have. A force distance graph. It says 5 data points were taken and plotted on the diagram. Draw the best fit line of the data. Okay, so best fit line of this data, if I draw it, is going to have to be a straight line that takes some of the points above, some below, and some through, right? Kind of. We know it's going to start at 0, so I'm just going to say it's going to do something along this lines, right through here, okay? You would do this with a much better job of this than I would because you're going to use a ruler, right? Yes. So now, if we have, first thing it asks is the spring constant. So we need to know what's the relationship between force and stretch. Remember, force is equal to kx, isn't it? Okay, so if this is on my y-axis and this is on my x-axis, then guess what this is? This is my slope. So that, and that, and that. So my spring constant is the slope of my graph. So let's find the slope of that graph. We're going to go through and pick 2 points. I'm going to pick this point right here, which I'm going to put an X on and say that this is 0.05, 25. And I'm going to pick one at the end, up here somewhere, maybe about right here. And I'm going to say that guy is 0.45 to 25. Okay? So now I'm going to take my slope, and I'm going to do the change in y over the change in x. So that is going to be 225 minus 25 over 0.45 minus 0.05, and I get a k, or a slope, that is approximately 200 divided by 0.4, which is 500. Remember, it is going to be force here, meters here, so it's going to be force newtons per meter, right? Okay. Now, how much work is done stretching the spring? Well, how much work is done? Well, we've got a force distance graph, and what did we just say on the previous page? Let's go back and look. Ooh, cool. So all we have to do is find the area under that graph between 0.3 and 0.5. So here we go. 0.3 is here. 0.5 is here. So what I need to do is I need to find the area here. So the work is going to be the area there. And I always state specifically area under the F versus X graph. Okay? So now, let's figure out what that area is. Hey, y'all, this should not be hard. You can break it into two pieces if you want. Okay? So, let's break it into two pieces. I'm going to take it and break it up right here. So I have a rectangle. So I'm going to call this area 1 and call this area 2. So area 1 is equal to 0.2 along the bottom. From 0.3 to 0.5 is 0.2. And its height here is 150. So 0.2 times 150. Plus then I'm going to do area 2, which is going to be 1/2 that same base of 0.2 times the height here from 150 to 250, which would be 100. So we're going to take 0.2 times 150. $30. This one ends up as 10. So we get a total of 40, and don't forget your units, joules. Okay? Now, suppose a 5 kilogram object stretches the spring 0.4 meters horizontally. The spring launches the object as the spring returns to its natural length. How fast will the object go upon being launched? Well, that one's an easy one because we know we can do that with energy. Mechanical energy in equals mechanical energy out. So we're going to stretch this spring. So we know we have start with spring potential energy, and it's going to convert to kinetic energy. So we're doing 1/2 kx squared equals 1/2 mv squared. So the first thing I'm going to do is get rid of that half, and then I'm going to plug in my amounts. I know k for the spring, we found that was 500. Stretching it by 0.4, and we get the mass is 100, what was mass? 5 kilogram. 5, and the velocity we don't know. So we want to know. So we solve this, multiply and divide and take the square root, and we get a velocity of 4 meters per second. So let's look at, all right. So we have a person pushing a 10 kilogram box up an incline that's at an angle of 37 degrees. Okay, let's not forget that typically sine of 37 degrees is about 0.6. Cosine of 37 degrees is about 0.8. Pretty close. Okay, so that's going to help us. All right, we've got a box up an incline that's angled at 37 degrees. Coefficient of kinetic friction, so we've got friction. So that is telling us that we have work due to friction. Between the box and the incline gives us that. Box is initially at rest. Person uses a force, so that's going to tell us something. Person uses a force, so we've got an applied force up the incline to push the box a distance. So we've got a D also. All right. So calculate the work performed by each of the following forces, including the correct sign. Okay. So the applied force. The work done by the applied force is going to be the force applied times the distance. So that one's the easiest one. We know the force applied is 120 newtons. The distance is 50 meters. So we're going to end up with 6,000 Newton meters, which is the same as saying 6,000 joules of work. So that is going to be positive. Okay? The weight force. The work done by gravity is going to be equal to F gravity but parallel times that distance. Well, now we got to figure out what F gravity parallel is. So let's do a free body diagram here. This guy is going to be going straight down. This is my mg, right? It's my force of gravity. But I know that if this box is going up the incline, that I need this guy right here and this guy right here. Okay, so gravity is working against it this time, isn't it? Okay, it is going in the opposite direction of the motion. Theta is up here, so this is going to be, this chunk right here is going to be the force parallel, so this is going to be mg sine theta. So let's put this in. So number one, we know it's negative because it's going against the motion. It's going to be mg sine theta times the distance. So let's plug all that in. We got negative 10, g is 10, sine of 37 degrees we said was 0.6, and the distance is 50. That ends up being negative 3,000 joules. So gravity's working against us as we try to go up a ramp. You know that one's the case. So now, last chunk. Let's look at the frictional force here. So the frictional force, work done by friction, is going to be the force of friction times the distance. Okay? So now let's draw in our friction. Our friction force is going to be going this way, isn't it? All right? Well, we also know we have to know for a force of friction, we're going to come right over here and say, we remember the force of friction is equal to mu times the normal force. So we got to figure out what the normal force is. All right, so let's figure out what the normal force is. So the normal force I'm going to do in red, which is here, that is going to be opposite, because those are the only forces, those three. That is going to be opposite this component right here, isn't it? So that one. And that guy is going to be mg cosine theta. So what we know is this is going to end up being mu mg cosine theta. So let's put this in. So we know this is negative, number one, because it is, again, working against the motion if this thing's velocity is going that way. So negative mu mg cosine theta times d. So let's plug all that in. Negative 0.25, 10, 10, cosine of 37 is 0.8, and d is 50. So this ends up being negative 1,000 joules of work. Okay? So, let's draw an energy bar chart based on this. So in the beginning, we have energy. We have applied a force, correct? So the only force we have in the beginning is the applied force, so this is our beginning, all right? So that's what goes on this bar chart. So we have some chemical, because it is actually applied, there's nothing else it really works with. So it's going to be 6,000, so this is going to go here. Purely pushing. Now, we are going to feed in, it's going to transfer to movement, which is kinetic energy. So some of that kinetic chemical energy is going to go there, right? Now, what's working against it? What's taking energy out of kinetic? That's going to be, arrow is going to be then towards dissipative, which is going to be friction, right? And towards gravity, because we're having to push uphill, okay? So this is my U sub G and F. That is going to result in the total that came into this picture getting smaller, if that makes sense. So let's split it up and say, we know, because we know this is going to be negative 3,000 joules, and this is going to be negative 1,000 joules. Notice it's going away from, not into, movement. All right? K is, of course, kinetic, which is movement. So now what do we have? Well, we came in with 6,000. We obviously don't have that anymore because we gave our push. So we have 1,000 in gravitational. I'm sorry, 3,000 in gravitational. We have dissipative of 1,000. So that's a total of 4,000. So what does that leave for kinetic? So if we take the 6,000, we subtract the 1,000, we subtract the 3,000, we're left with 2,000 joules for kinetic. So this guy goes here, okay? And that's what our picture would look like. So now it wants to know the final velocity. Well, if I know the final velocity, I know that my kinetic energy is going to be 2,000 joules. Well, kinetic energy is going to be equal to 1/2 the mass times the final velocity squared. So now I'm going to take that 2,000 and set it equal to 1/2 the mass of this block, which is 10, times the final velocity squared. Multiply by 2, divide by 10, we get 400, take the square root, and we end up with the square root of 400, which is 20 meters per second. Ta-da! Okay, so now let's suppose again that the student pushes the box down the hill, starting from a rest at a distance 50 meters with a force of 120 newtons applied parallel to the incline, okay? What would the box's final velocity be? Now, all of you can hopefully figure out that it's going to be faster than going up the hill. Why is it faster? Okay? Well, here's the deal. We already know what all of these are. What's the only thing that's going to change? If we're going down the hill, the applied force isn't going to change. The weight force is not going to change. Oh, but it is. Because now, if we're going down the hill, then the weight, this component of the weight force, which is mg sine, is not working against it anymore. It's working with it. So what do we know? We know we're going to put in 6,000 is going to be in 6,000 joules. Now, kinetic is here. We're still going to, except what are we going to do here? Gravitational is going to put in 3,000 joules because it's helping us, but we're still going to lose dissipative minus 1,000 joules, right? So do you see the difference here? The arrow, which way the arrow is? The arrow is pointing towards kinetic energy because it's going to be helping, okay? So what do we have here? We now have the original 6,000 joules plus 3,000 this time minus the 1,000 joules. We end up with a net 8,000 joules of gain. Right? So now we set that kinetic energy, which is 1/2 mv final squared, equal to 8,000 joules this time. And what we end up with is a velocity final that is 40 meters per second when we finish. Okay? I want you to think about that. Just that one change in the arrow. And the big thing was, the big change in the arrow was this guy right here. It was going out, and instead now it's helping, so it's coming in. All right, I hope that made sense. Energy is important. And all right, roller coaster example. A roller coaster car carries a single child, has a total mass of 100 kilograms. So we've got a mass of 100 kilograms. It's moving very slowly at point A. So it's pretty close to zero. At the top of the first track. So we know it's at the top of the track. net force acting parallel to the track is represented by F parallel. Okay, so we can see on our graph that we have F parallel here. So this is my F parallel side, okay? So I have a force displacement graph. Ooh, that's cool. Strength of this force is shown on the graph. We know that. As a function of distance along the track, where the forward net force is positive. So if it's forward net force, it's positive. If it's negative net force, it's not positive. Only individual forces acting in the car are the weight force and the normal force, not the force of friction. So no friction. All right, determine the net work done on the roller coaster between 0 and 100. So net work between 0 and 100 is area under an F versus X graph. So we need to figure out what that area is. So work is equal to 1/2 the base here, which is 100, times the height, which is 400. So that is equal to 20,000 joules. Okay? Now, is the network found in part A due to the normal force only, the weight force only, or do both forces do some work? Well, I want you to think about normal force. If the car, normal force is always what? It is always perpendicular, isn't it? To the motion. So does it do any work? Nope. Remember, perpendicular to the motion, it has to be parallel, not perpendicular. So no, it has to be what? It has to be the weight force only, guys. Okay? Weight force only. Okay, so it's going to take, so we're going to have 2,000 or 20,000 joules of what? It's up the top of the hill, so gravitational potential energy, and it's going to convert to 20,000, since it's no friction, joules of kinetic. Does the car move uphill or downhill as it travels from position 0 and position 100? Well, if it's at the top of the track at A and it gains energy, what do you think? So it's at the top of a hill and gains energy. It is going downhill, okay? So how much downhill is it going and how much energy? What's the change in height for the car? Well, we know it's 20,000 joules, and that's equal to U sub G, which is mg delta Y. Well, we know what M is. So we've got, what, 20,000 equaling, the mass of this thing was 100. Gravity is 10. So delta Y, solve for it, and you get a delta Y of 20 meters. So it is going 20 meters downhill. So now, as it goes from 100 to 200, well, as it goes from 100 to 200, it is now what? It is now got a negative force. So it's got a negative force, which means it's got a negative area. The area under the curve is negative this time. So the work is negative. Okay? If it's negative work, it's losing energy. Right? Okay, so if it's losing energy, it must be going Can't be going downhill. It was gaining work, so it must be going uphill. Now, what is the area? So let's find that area. -1/2 what? I'm going to change colors so you know what I'm doing. This is 100. This is 200, right? -200. So we got 100 times 200. So this ends up being -10,000 joules. Okay, so -10,000 joules means what? Well, let's set it equal. -10,000 joules is equal to mg delta y. So -10,000, mass is 100, gravity is 10, delta y. So we have a delta y exchange of -10 meters, which means it gained 10 meters. It went 10 meters, what? Up the hill. So 10 meters uphill. All right. So now draw the roller coaster track to the right. We said it started at 20 meters and then it went down to 10 meters at B. So this is point A. This is point B. So it went down the hill and then it finally got to here at point C. What is it doing? Okay, at point C, it's now gotten to the bottom of the hill. Then we said it started going uphill, but it didn't finish until uphill until point E, but it didn't go as far. It only went 10 meters up at E. So we'll say this is E, so it has to go back up the hill to E. So D has to be somewhere in between, okay? So D is here. Okay? There we are. So here we go. Let's draw the energy bar chart. We started with 20,000 gravitational potential. At point B, we knew we had gotten to what? The top of the hill? So now it's moving, or no, it was at the top of the hill. It's halfway down the hill, approximately halfway down the hill. We see that here, so it's got to have both. It's got to have, if it's gone about 10 meters, then at point B we could figure out exactly what it is too, because it's got to be, point B is exactly half the area, isn't it? So half the area would be half the work. So yeah, it splits that 20,000 into 10 and 10. Okay, so now it gets to the bottom of the hill, and the bottom of the hill means that it has no gravitational left, which means it all converted to kinetic. Now at point D, it's going back up the hill. Now it is not going to go as far. It is not going to go as far here, so I'm going to skip over here and say it's going to be here. But there is no friction, so some of that energy had to go somewhere, which means it had to be, the other half of it had to still be, so it's still moving at the top of the next hill. So what happened? That means that it had to have split somehow. Well, I'm looking right here, and I'm looking at the area, and this is exactly half the area again. So if the area was 10,000, I know this has to be, again, half the energy, the net energy has to be in gravitational, correct? Well, in kinetic, excuse me, because it's moving uphill. Half of it's lost in kinetic. So what we know is that this thing is gaining half here, and what it gains there, it loses in the other column. So it goes from 20,000 down to 15,000, and then continues to lose as it goes the other half, right? So this would have been 5,000 joules net, -5, and that would have been from kinetic. So it comes out of this and goes into that. And then here it would have lost another 5, coming out of here and going into there. Okay? I hope that made sense. All right. So let's finish up here. We got an example here. Mass is 2 kilogram compresses a spring of force constant 800 newtons per meter. Distance 0.2 from its natural length. When the block is released, it travels down a rough incline. So we know initially, so mechanical energy initial, and I'm going to draw mechanical energy final, right? We know it's conserved, even if there's friction. Oop, there was work done by friction. So what do we know? We know it starts at rest, so kinetic energy initial is 0. But it starts up, it has a compressed spring, so it has spring potential energy, doesn't it? Starts at the top of a hill, because we see H here, so it has gravitational potential energy. All right, and we're going to do friction, so we have work due to friction, which is going to be negative. Okay? Now at the end, it is at the bottom of the hill, so it's moving, so K final, we have U spring is gone, because it's not on a spring anymore. U gravitational is gone, and friction is gone. So there is no work due to friction. That was only in this column. So let's write this statement out. We have U spring plus U gravitational minus the work done by friction, because it's negative, equals K final. And that's how that works. So we have 1/2 kx squared plus mgh minus the force due to friction times the distance it goes is 1/2 mv final squared. Oh, how much work was done by friction? You know what I can do then? I can leave this as just work due to friction. We can make it plus because it'll come out negative. Okay? Since we're finding that work due to friction. So what do we get? Let's plug in. 1/2 K was 800. It compressed it how much? 0.2. Mass is 2. Gravity is 10. The height of the incline is 4 meters. Work due to friction. 1/2 the mass, which is 2. Final velocity is 2. We end up with work due to friction being negative 92 joules. And we knew it needed to be negative because it was bleeding off energy. Example. We've got 2 examples here left to go, guys, and then we're done. Hang with. A spring hangs vertically. All right, so we've got a vertical spring hanging. And they let it rest. They hang a block on it. So it's going to stretch, isn't it? So we need to know what the distance is between those two. Oh, it stretches the spring 0.2. So I know the distance from here to here is 0.2 meters. Okay? I know this is 3 kilograms. So I know that much. So now, the block remains at rest once it stretches. Okay? Is the mechanical energy conserved during the process of lowering the block from unstretched to equilibrium? And it wants us to show during the calculations. So first things first, do we know the spring constant? And the answer is no. So to do this, we're going to use forces. okay? Anytime you need a spring constant, forces is easiest because we know this is going to be what? Kx this way, and we know this is going to be mg this way, okay? So to get k, we're going to set kx equal to mg and solve. So we got mg, which is 3 times 10. We don't know k, but we do know x is 0.2. So we're going to get a k when we divide, that is 150 newtons per meter. So there's my k, because we're going to need that for energy. So this thing starts with what? Spring potential, doesn't it? Use of S. It's going to start with some spring potential energy. What is that spring potential energy going to be? Based on the stretch, 1/2 kx squared. So 1/2 that 150 times that 0.2 squared, and we get a spring potential energy of 3 joules. It's going to gain 3 joules once it stretches, okay? Now, it is, however, going to lose gravitational potential energy, isn't it? Well, gravitational potential energy is going to be mgh. Well, m is 3, g is 10, and the h is 0.2. That, folks, is 6 joules, and that's what it loses. So, do a comparison. 3 joules gained versus 6 joules lost. Is it the same? No. Not conserved. Matter of fact, we could figure out what it did. If it lost 6 but it only gained 3, then it did negative work. Okay? Last example. Students performing experimental trials in which a piece of clay of m, mass m, is launched. Initial rightward velocity v naught from an initial height h. You can see that in the picture. It's launched to the right. All of the velocities to the right. In trial 1, the clay is shaped such that the force acting on the clay due to the air can be ignored. Okay, so we know it's not going to be like super floppy, more like a bullet than a big ball. Okay. In this trial, the horizontal distance traveled by the clay before striking the ground is d sub 1. The speed of the clay just before striking the ground is v sub 1. It says in each additional trial, draw a greater than or less than or equal to sign in the blank to explain your reasoning. So now, in trial 2, the clay is given a new shape. So now, the clay experiences a constant leftward force due to the air for the entire time the clay travels at the projectile. Okay, so what does that mean? That's air resistance, isn't it? If it's going to the right, and the leftward force is to the left, so it is doing, it's got a negative work due to friction or drag, right? So that is going to mean that it will not travel as far, nor will it travel as fast. So why? Leftward force on a rightward moving object. So in other words, you have acceleration is negative and velocity is positive. So it is going to slow down, right? From original velocity, okay? It's working against it, correct? So, now, if the velocity 2 is less than velocity 1, we know that the final distance, right? That distance is going to be v sub 2 times t. And so this would be, x final would be d, wouldn't it? This would be d sub 2. Then d sub 2 has to be less than d sub 1. Correct? Because they have a direct relationship. Okay, last chunk. Now it's given a new shape so that it experiences a constant upward force due to the air for the entire time that the clay travels. All right, so an upward force means that what's gonna happen? This one's weird because the work due to that upward force is 0, okay? But what does it mean? If you've got something going this way, but you have it going that way also, that means it's going to end up going this way, which puts it in the air longer. Think about it. If it's normally falling at a certain rate, right? Then what happens? It is going to fall at less than g, isn't it? So if it falls at less than g, it takes more time to fall. So it goes further. So this is bigger than that. But is it going faster? There's the question. So let's look and see. What do we think? So this thing is going to go further. And up in an angle. It's going to fall, oops, further. Let's do the better job of our picture here. So it's going to come in that way because it's going to have less of a y and more of a what? Actually, it's going to have more of a y. Now it's going to actually have a y and an x.
Good afternoon, Austin.
Okay, so the easier way to represent this might actually be to say that we know that it has... Okay, so let's think about this practically. If it has more time to fall and it goes further, that means it must be going slower. Okay? So that's going to be that way. Has to be slower. Okay? And think about what that means. In terms of forces, we've got this thing traveling this way, correct? Okay. But what do we know? We've got a force of the air, which is going this way. But it also has it's going to lose energy. So the kinetic energy goes down. And if the kinetic energy goes down, then the velocity goes down. All right. Hopefully one of those explanations makes a little more sense to you. If you have a better explanation, hit me with it, dazzle me. Okay? All right, this is the end of the notes for this section.